So this is Generalized Linear Models with Examples in R. That book right there. We're in Chapter 3. Still plugging away here. We're on question 20. And yeah, so not much to say about it. We'll just go through everything one at a time. Okay, so it's based on a data set called wheatrain. And we'll look at the data here in just a second. But roughly we see that that the data set kind of has data containing average rainfall, region, altitude, latitude, longitude. Okay. So let's get into that. So first you need to install and load the GLM's data package, and then you need to call up the data or the wheatrain data set. And I'm just calling it D here, and we can take a look at it. Right. So we have these different stations, must be weather stations or something, and we have altitude, latitude, longitude, average rainfall, and region. Okay, so when I look at region here, I realize I don't really know what region is meant to signify. So I want to investigate what region is, because I think that we're going to have to use it at some point, and these numbers don't really tell me much. So if I go to question mark wheatrain, I can pull up the data file on that. Okay, so it's right here. Okay. And so we see that that it is a station's region. So it's here's station over here, the first column in the data set, as computed by Bower et al. 1993, using principal component analysis based on monthly rainfall, a numeric vector with levels 1, 2, 3. Okay. So I don't know what any of that means. So so I do know a little bit about principal component analysis, and it's probably a little bit too much to explain here, but just based on this wording, it could be that these numbers here actually mean something, that 2, whatever region is, 2 is bigger than 1, although I don't know that it's twice as big as 1. Or it could be that these are just arbitrary labels that have been given here, and I really don't know which. So I am going to treat it as a factor where 1 is just a label. I don't know if this is appropriate or not. So if you don't do that, you will get different answers than what I'm getting. Okay. So to convert region to a factor, I just grab that variable and I say as factor region. I've already ran this, but I guess now we can just see what this looks like. Okay, so we have region, and it's the same values, but now we have 3. Now it's called a factor. Okay, but it's the same values. But now R sees these as labels rather than as numbers. Okay. Okay, so now we're on to the first part, to 1, and we're supposed to plot annual rainfall against region and altitude. Identify any important features. Okay, so to do this, I'm going to plot average rainfall against altitude, and then I'm going to signify the regions by changing the markers to correspond to different regions here. Okay, so we pull that up. All right. So I don't know which marker corresponds to what region, but you have the 3 different regions, 1, 2, and 3, and you have average rainfall as a function of altitude. So is there any important features? I mean, I don't know. I mean, it looks like a pretty linear relationship to me. It looks like one of the regions, I don't know what number it is, but it's makes up just one part of kind of one part of the line, this imaginary line I can see through here. There may be some heteroscedasticity. It's a little bit tough to say though. Okay. So next we want to interpret a regression model that has a systemic component, alt times region here. Okay. So I don't. This question is always very vague, and the few times that the back of the book answers have answered this type of a question, they're very generic answers, and so I don't know what else to say here other than it just says the average rainfall is a linear function of altitude and region. That has it would be altitude plus region plus the interaction between the two. I don't know really what else to say with that one, but so okay. Part 3, So we're going to fit the model with systematic component AR, or average rainfall being regressed on alt times region, the one that we just discussed here. Show that the interaction term is not necessary in the model, but both of the main effects are necessary. Okay, so let me point out just a couple of things here. First of all, the way that this is worded makes me think that to convert region to a factor may have been not correct, but I really don't know. So I think you would be justified in not having converted it to a factor. But this is where the differences are really going to start to show if you did not convert to region to factor. Okay. So now also, I really struggle with some of the vocabulary in this book, or some of the phrasing in this book, because what does it mean to need, or that something is necessary in the model? Okay, so I kind of go through some ideas here. So by need, if what is meant by need means that it fits the data better than any other model on offer, right? Then we could say that the interaction term is not necessary if one or both of the following conditions. The interaction terms in M3, which is the interaction model that I've defined down here, is not significant, but the main effects are, and that an F-test comparison between M2 and M3 finds that the additional interaction term that is included in M3 does not significantly improve the fit. Okay, so I ran M2, which is no interaction, and M3 with the interaction, and we can look at these. Okay, so it looks like the top one here is M2. Okay, so we have our coefficient values for altitude, and then region 2 and 3. Okay, so because we've converted region to a factor with 3 levels, it takes the first level of that, region 1, and sets that as the default, and then establishes the coefficient values based on that one being the 0, basically. How different is region 2 from region 1, etc. So you could conceive of a situation where region 2 is a significant p-value, and region 3 is not, and then now it gets a little bit confusing as to whether or not the main effect was really there or not. But anyway, so we have that the main effects, fortunately, are significant. Okay, and then if we go down here to M3, where we've added the interaction terms, we see that actually nothing is significant. Okay, so that's a little bit confusing, but if we take the ANOVA, if we run an F statistic between these two models here, okay, so here's M2 compared to M3, okay, well, we see that by adding the additional interaction terms does not significantly improve the fit. And so we might say then that the interaction term is not necessary. Okay. Now, there's another part of this, which is we're supposed to show that the main effects are necessary. So we have to run a similar comparison, where we have the main effects compared to no main effects. In other words, just an intercept. Okay. So if we run our intercept-only model and compare that to M2, hopefully M2 is doing a better job of fitting the data. And that, in fact, seems to be the case here, right? So adding the main effects does a better job. And we might also want to know if both main effects are necessary. So now I have just the altitude main effect and just the region main effect, and then again we can compare these to M1 and M2, or we can compare both of these to M2, and hopefully M2 is doing a better job than both of them. And in fact, so that's the case here, right? So M2 is the second model, and in both cases it's significantly improving the fit of the model. So again, it seems that both of the main effects are probably necessary. Now, but what if we don't mean which model is the best best fits the data? Well, then, but we want to know instead which one is most likely to fit out of sample data. Well, now we need to do something, use some kind of information criteria like AIC here. So we can just get all of the AIC values for the different models, run these, and so M2 is the fourth one on here. Okay? and we see that M2 is in fact the lowest. So that gives us, more confidence that M2 is good, the best of these models. Okay, but there's still a third way in which we might talk about need, or the main effects being necessary and the interaction being unnecessary, and that is, if we are subject matter experts in all of this, we may really strongly believe that there is an interaction term, and just because our sample does not bear that out, our test on our sample does not bear that out, does not necessarily mean that an interaction term does not exist. Okay, and so we may insist on leaving in an interaction term if we have good reason that exists outside of our available data that it should exist. So, yeah. Okay, on to part 4. All right, so we are going to produce diagnostic plots and evaluate the fitted model, which I take to mean M. I'm not sure which one. Let me clarify this. Yeah, so I'm not sure. So the way I am interpreting this, diagnostic plots to evaluate the fitted model. Well, what is the fitted model? Well, the fitted model, I believe, is M3 with the interaction term in there, even though we've been asked to show that M3 was maybe not the best model, but that's fine. Okay, so we can, so first of all, we can make some diagnostic plots here, just with the plot function, okay? And we're supposed to identify the observation that appears to be the outlier. Well, that is clearly number 13 here, right? There, okay, there, right? So it might be a little bit difficult to call it an outlier given these views, because we see that it's not surpassing any of these thresholds on the residuals by leverage plot. But also these plots use the standardized residuals, and we're asked to also use studentized residuals. Now, what's the difference? Okay, so remember, a standardized residual basically puts all of the residuals on the same scale. The studentized residuals do the same thing, but each residual, the residuals of each observation, is found by having omitted that observation and then fitting the model to the rest of the data and looking to see, how far off that the omitted data point is from the model that was fitted with the data not including it. So, anyway, so we want to make maybe a couple of analogous plots here. So I'm taking our student M3 to the fitted, and I also have just the standard residuals here, and I'm plotting both of them. And so the black ones are the student residuals, and the red ones are the standardized residuals. And you see that these are all pretty close, but that the studentized residuals for the offending observation here does make kind of a big difference in terms of the size of the residual. So for instance, if we were, so what we've built here is like this upper left-hand plot, and so that, not exactly, but it's like that. And so this residual right here might be larger. So anyway, so in short, observation 13 seems to be the odd one. I wonder if it's not this one right here. It's hard to say. Okay. All right. Okay, part 5. So the data are spatial. So in other words, these weather stations, they exist somewhere on the face of the Earth, and so they have some kind of spatial relationship. So we are going to examine the independence of the data by plotting the residuals against longitude and latitude, and then comment. Okay. So I'm going to plot the studentized residuals against longitude and latitude. And so this is kind of a cool little feature of the plot function. I can get all the plots I want from the linear model. On a two-dimensional plot here, you can only show, two of the two axes, right? So you can get both of these plots. I took a little pause there, so I've kind of forgotten where I left off at. But anyway, so we can get all of the plots of these residuals for longitude and latitude here. Okay, and now I'm also recreating these plots one at a time, right? Instead of using this notation right here, and then so here I have the residual based on longitude, and then I am setting the size of the marker to latitude, and then conversely, I have the residual for latitude where I'm setting the size of the marker to longitude, or a scaled version of that, to see if there's any additional patterns here. And really, to my eye, I don't see any patterns. So anyway, so there we have it. So I don't think that there's anything interesting going on here. If I squint my eyes, I might think that there is some kind of parabolic relationship happening with the residuals against longitude. I could even test that. So I could take my residuals here and regress them against a parabola, basically, against longitude, and look at the summary. And it doesn't seem, if you look over here, it doesn't seem like there's a lot of evidence for that being the case. So, all right. Yeah, but I leave a little note here about why I would be surprised if there was any kind of parabolic relationship. But anyway, so so lastly, we want to summarize the diagnostic analysis of the fitted model. So again, I'm not really sure what to say about this, but I'm not entirely sure what is meant by. I'm not sure which which fitted model we're talking about at this point. I feel like about 2/3 of this question has been summarized, the diagnostic analysis of the fitted model. But yeah, so like I said, I don't really know how else to expand on anything that we've done so far.